Hello everyone, and welcome to session number 7 of this set of videos created to explore programming applications in reinforced concrete. In this session, I will present a Python standalone application developed for the flexural analysis of rectangular doubly reinforced concrete cross-sections. Standalone means that you can run the code on a computer even if Python is not installed on that device. The way a standalone application is produced in Python: first, you need to write the code, then test it thoroughly to find out whether the code is ready or still needs some corrections. Once the code is ready, then you can use a Python package like PyInstaller to convert your code into a standalone application. Compression steel is usually added to a reinforced concrete beam in order to increase ductility, change the mode of failure from transition controlled to tension controlled, and to reduce long-term deflection of the beam. The folder on screen contains the standalone application that I created, as well as two text files. One of them is the input file and the other one is the output file. The user inserts all the required information into the input file, then double clicks on the standalone application to generate the output file. Let's look at an example. This here is the input file. The information required from the user include width of beam, depth of beam, yield stress of flexural steel, compression strength of concrete, diameter of bar in the farthest layer of tension steel, diameter of bar in the second layer of tension steel, diameter of bar compression steel, number of bar in farthest layer of steel, number of bar in second layer of steel, number of bar for compression steel. Then we have N cycle, which is the number of cycles required for the iterative procedure to produce Fs prime, which is the stress in the compressive steel. Then we have concrete cover and the diameter of stirrups. The user clicks on Save after inserting the required parameters, and then double clicks on the standalone application to generate the output file. Once the output file is generated, we can double click on it. The output file shows the time the analysis was conducted. Then we have a list of input parameters, the parameters that were inserted by the user. Then the application calculates all the necessary calculations. If the steel in compression did not yield, as is the case here, then the application performs cycles in order to calculate Fs prime. The calculations continue. The cross-section is checked for adequacy, and if the cross-section is adequate, then the application prints out the design strength of the cross-section. Let's go back to the input file and change a couple of parameters in order to produce a cross-section where the compression steel has yielded. In the example that we have just conducted on screen, you can see that the compression steel did not yield. So we're going to close this output file here, go back to the input file, make a couple of changes. 25 millimeter diameter for the second steel in tension, 12 millimeters for the compression steel, tension steel 4x4, and change the number of cycles to 10. Let's hit save and then double click on the standalone application in order to update the output file. Again, here we have a listing of the input parameters, and here the application performs all the required calculations. We can see here that this section, the compression steel did yield, but when the application performs the adequacy check, it turns out that this section is in the transition zone, and thus it is not acceptable by the ACI code. I have added a couple of if statements to the code for the doubly reinforced concrete cross-section in order to make sure that the information inserted by the user is reasonable. For example, the number of bars in the layer farthest from the neutral axis should not be less than 2 bars. The diameter of bar in the layer farthest from the neutral axis should not be smaller than the diameter of bar in the layer next to it. The number of bars in the layer farthest from the neutral axis shouldn't be smaller than the number of bars in the layer next to it in order to have an efficient use of steel. The number of bars in the second layer should be greater than or equal to 2. We cannot have 1 bar in the second layer or 1 bar in the first layer. And since this one here is a doubly reinforced concrete code, then the number of bars in the compression steel should be at least 2 bars. Let's have another run, but this time deliberately mess up the numbers in the input file in order to see what the application is going to do in that regard. Let's insert the diameter of bar in the layer farthest from the neutral axis as 22 millimeters and leave the diameter of bar in the second layer as 25, which is not very efficient. Then I'm going to insert 1 bar here in the layer farthest from the neutral axis, leave the second layer as 4 and insert 1 bar for the compression steel, and I'm going to change the number of cycles to 8. I'm going to save the file and double click on the standalone application to generate the output file, and let's look at it here. We can see here the listing of the input parameters, but if we pay close attention we will see that the application has switched the diameter of bars. Now you can see that the diameter of bar in the layer farthest from tension is 25 and the layer next to it is 22, although this is not what I inserted here. And you can see that the number of bars in the layer farthest is now 4, although here inserted as 1. When it is corrected to 2, the number of bars in the layer farthest will be smaller than the layer on top of it, so the application switches the bars in tension, and the number of bars in compression is changed into 2. Not just that, the application also states what changes have been made to the input that the user inserted. What is next is the calculations of the required parameters. Here the compression steel did not yield, so the iterative procedure is initiated. The section turns out to be tension controlled and the design strength is printed out. We can compare the performance of this standalone application produced using Python to that of the Maple template that I showed you in the second session of this recorded series. This here is a Maple template that is generated to perform analysis of doubly reinforced rectangular concrete beams for flexure. If we insert the same input parameters for the first example that we ran in this session, session number 7, here in Maple, and click run, then we obtain the results here. As you can see, Maple produces all the required results, checks this section for adequacy. It turns out that the section is adequate, and then it prints the design strength, which is identical to that for the first example that we ran here in session number 7. Maple also plots the cross-section, the ductility status of the beam, and shows the convergence of the iterative procedure. I will show you in subsequent sessions how to produce plots using Python. This concludes our session for today. Thank you very much for being with me, and I hope that I will see you in subsequent sessions. Best wishes.